So graph sketching is actually a GCSE topic, but it doesn't come up that often in GCSE, so we're going to go over it and highlight all the key features just so that everybody knows. So, we have got, these are all what I would describe as outside transformations, because we've got f of x here, the graph, the original graph, and the transformation is happening outside of that f of x, okay?
Yeah.
So, we've got the first one, sticking a minus out the front. What that's going to do is reflect it over the x-axis. So this original graph would end up like that. So if this is f of x, then this is minus f of x, okay? So that's quite an easy one. We've got minus a, that moves it down. However much a is, yeah, so it starts here, and if you want to move it, f of x minus 2, you go down 2, or f of x plus 2, up 2, not complicated. If you want to stretch it, so f of x, let's move this one out of the way. If we wanted to do, for example, 2 f of x, then what happens is that you get a stretch, and this bit, you have to learn this bit. Parallel to the y-axis means this is the direction of the stretch, like a y-axis. So we're stretching that way, and about the x-axis means that the x-axis is kind of pinned down. So anything along here gets pinned down and fit, almost like you're putting drawing pins in.
Yeah.
And then you're pulling, like elastic, the graph away.
Along the
y-axis. Along, parallel to the y-axis, and all of these are stuck down, they're all pinned down. So this gets stretched this way, this gets stretched, this gets stretched, they all get stretched away.
Except
like that.
these points.
The one down here, it gets stretched, but because that's been pinned down with a drawing pin, it can't move.
Yeah.
So everything gets pulled away. So we might have, if we have scale factor 2, for example, 2 f of x, then this would get twice as far away. This is pinned down, so it can't move. This is pinned down here, so it can't move. And then that would be twice as far there. So everything's getting twice as far away from the x-axis.
Mm-hmm.
Okay. So that's the 4 types of outside transformation. What happens to the actual coordinates? Now, this is important because you get exam questions like this and you need to know how to lay it out. So, the x-coordinate does not change. The x-coordinate does not change, the x-coordinate does not change, the x-coordinate does not change.
So on outside, transformation to x-coordinate doesn't change.
Yeah. So, what we know is that the coordinate is going to change, but not the x-coordinate. That is not going to change at all. So it's a good idea to just put them in first and think to yourself, they are not changing. And then think, right, what am I going to do to the y-coordinate? So in the first example, where we're reflecting it, so it's going to end up like this, reflecting it like that over the x-axis, it's the y-coordinate that changes sign. So 0, 0 stays at 0, 0, 4, 0 stays at 4, 0, but 3 minus 2 ends up at 3, 2. So what we're actually doing is the y-coordinate is changing sign. If it was plus, it was minus. If it was minus, it was plus. So you can think of it in the 2 ways, a reflection over the x-axis, but also what's happening to the individual coordinates so that you can then, on your sketch, plot them correctly. Mm-hmm. Okay, let's look at the second one then. Again, those x-coordinates are not going to change, so I don't even need to think about that at all. So in the second one we're going to, what are we doing in the second one? Oh, I've rubbed out my original. We're going to move it up a.
Yeah.
So the y-coordinate is going to have a added on.
Mm-hmm.
So in this case, 0 add a is a, 0 add a is a, minus 2 add a is minus 2 add a. Depends obviously what the a is. So they would be the new coordinates. The graph, which I've accidentally rubbed a bit out of, but never mind, would go up a, however far a is, and we would know what the new coordinates were going to be. Similarly, if we were doing f of x minus a, the graph, instead of going up, goes down, and we would simply have minus instead of plus, exactly. So we would say what's going to happen is that y is going to have a take method. In the situation, that last one, where we've got a stretch, and the stretch is parallel to the y-axis about the x-axis, and the scale factor is a, so what's happening is that the y-coordinate would get times by a. Or, yeah, basically times by a. So 2 f of x, y coordinate gets doubled, half f of x, y coordinate gets halved. Just does exactly what it says it's going to do, basically.
Yeah.
So the y coordinate is going to get times by a. In this case, 0 times a is
Zero.
not a, it's 0.
And that's why it gets pinned, isn't it?
Yes, it's fixed here. So
So
when
when you've
you,
got 0 times 0, times anything, you still get 0.
yeah, it doesn't move, it's fixed. Same thing on that second one. On this third one, you just multiply them together, depending on what a was. So there's what we do to the actual graph, the description, particularly you need to learn this last one, all those words, and then there's what we do to the individual coordinates. So these are all outside. Then we can look at inside. Do you know who this guy is? Mr. Topsy-Turvy, because inside is topsy-turvy. Everything is the opposite of what you think, really, apart from the first one. The first one, you can see the inside in the sense that we are inside the brackets. That's the sense in which it's inside. Instead of being outside f of x, it's like we've climbed inside f of x, inside the function, and that's where we're changing it. So all of these inside ones, they affect the graph left and right, whereas the outside ones are up and down. So instead of reflecting up and down over the x-axis, we reflect left and right over the y-axis. So this graph would look, oh, I'm struggling to draw it. It would look like that. Yeah, it would reflect over that way, and that would reflect over that way, basically. We could also, I bet I'm going to rub my graph out now, aren't I? Never mind. We could also shift it. Now, this is the sense in which it gets a bit topsy-turvy. You'd think that would be right because it's a plus, but it's not. It's topsy-turvy, it goes left. So just the whole graph picks itself up and moves left, however far you need to go. Similarly, topsy-turvy says minus, you'd think it was going left, but it's not, it's going right. So as long as you remember it does the opposite, that rule will kind of see you through, basically. So that goes right. And then here as well, topsy-turvy, you'd think, for example, f of 2x was going to double, but it's not, it halves, does the opposite. So it's a stretch, same as 2f of x would be a stretch. This time it's parallel to the x-axis, so this is what an x-axis looks like. So the stretch is like that. About the y-axis,
So point to the y-axis fixed.
Everything on the y-axis is like pinned down and fixed. This is all fixed, and then the stretch happens away from that point. So if we did f of 2x, then what it's going to be is it's going to not pull away scale factor 2, it's actually going to have scale factor 1/2. It's going to halve everything. So it would look like this, the blue graph. So everything's halved what it was before. Everything's come in by half of what it was before. So it's the opposite of what you think, always the opposite. So if it said f of a half x, that's not going to stretch scale factor 1/2, it's going to stretch scale factor 2. Because that's
1 over 1.
yes, upside down. So just do you know what that scale factor would be? It's not 3 over 2.
It'd be 2 over 3.
Excellent, 2 over 3. So the scale factor here is 2 over 3, the opposite of what you would think. So 1 over 3 over 2 is 2 over 3. So again, what happens to the coordinates? Well, the y coordinate is not going to change. Y coordinate does not change, y coordinate does not change, y coordinate does not change. So we can straight away, whenever we're doing one of these transformations, just fill in the y coordinate and make sure that you don't change it. And then think, what happens to the x coordinate? What am I actually doing? Well, the reflection one is fairly easy.
Making every x be negative.
The x changes, exactly. So it'd be 0, minus 4, minus 3. That's fairly easy. And then it's a reflection, and then you can fill in the coordinates. The second one, again, fairly easy, just remember it's the opposite. So the x1 would have a taken off for f of x plus a.
Yeah.
So this would be minus a, 4 minus a, 3 minus a. The next one, f of x minus a, you think you're going to subtract, but no, you do the opposite, you add. So it would be adding a to everything. And then again, you do the opposite, you think you're going to times by a, but you don't, you divide by a. So this final one, the coordinates would be, well, 0 divided by a is still 0. 4 divided by a, 3 divided by a.
So here's a question then. In the last slide, you had it as 1 over a. Why is that the same with the divide?
That's a good question. Okay, so you're saying that for example, with f of 2x, I said the scale factor was 1/2, and so you multiply by a half to get the new coordinate.
Yeah.
And now I'm saying divide by 2.
Yeah.
Yeah. And so it looks like the rule I've invented is that you take that number and divide by it. And actually, you can do that because it's the same thing. Because when you multiply by a half, if you've got a number x times 1/2. Now, this is what I was saying earlier about, on the previous video, I think, about when you've got fractions, you times the tops and times the bottoms.
Yep.
If you've got a whole number and a fraction, sometimes it's not clear what's happening. So we write the whole number as a fraction, x divided by 1, times 1 over 2, times the tops and you get x, times the bottoms and you get 2.
Which is x divided by 2.
Which is x divided by 2. So timesing by a half is the same as dividing by 2. And actually you can extend that. So timesing by, let me work this out, so I've got some room. Timesing by any number is the same as dividing by its reciprocal. That sounds complicated, but it just means, for example, timesing by 3 over 2 is the same as dividing by 2 over 3. Which I think you've seen in GCSE when you have fractions and you want to divide by the fraction, then the way that we do that is to change it to times and turn the fraction upside down. So it's just bringing all the GCSE ideas together, really, and becoming more fluent with them. So we've got inside and outside. If we go back, we've got the outside ones which do exactly what you'd think they do, learn that final sentence. And then we've got what happens to each coordinate when you do an outside transformation. We've got inside transformations, the fact that it's topsy-turvy does the opposite of what you think, and then we've got what happens to each individual coordinate in that type of transformation. And so you're going to actually fill in your booklet, if you haven't done so already, this information. Outside is nice, and also the outside, if you forget which way round it is, think of outside as the clouds, looking up at the clouds, so you're looking vertically upwards for outside to the clouds. So these are all the up and down transformations, and the topsy-turvy one, that's the one that's inside, that's the one that's all back to front. So we're going to look at some examples, just really quick, moving them up, down, left, right, that sort of thing. So if I move the graph, you see if you can write down what it would be. So let's do an outside one. So if we move the graph maybe down 2. So this is outside, so x squared should be preserved. Excellent. So the x squared is here.
Yeah.
And we are outside of the x squared, exactly. So really easy one. This one here, that's moved up 3.
Like x squared plus 2.
Yep, so x squared is preserved and there it is outside. What about, I'm going to have to draw this one on. What if I stretch it, and I don't know how to stretch it. I'll do a stretch like that, so everything's got bigger, and I'll say that I've done scale factor 6/5, I think. That was my stretch. Scale factor 6/5, everything's 6/5 as big. Yep, perfect. So there's the x squared, still preserved. We're still outside of the x squared. And then the obvious one. You'll know that graph. Yep, minus x squared. X squared here. We are outside x squared. And the transformation flips it upside down. Perfect. Okay. Apologies if you can hear the builders banging in the background there. So let's do some inside ones now. Just going to move him so I don't help him out accidentally. I don't know why I'm calling a quadratic graph him, but never mind. Okay,
It's more of a her, but then.
okay, so there's the graph. So let's move it left 2.
Left 2.
Left 2. Perfect. perfect. So we've gone inside that x squared now, in with the x,
Yeah.
and done the opposite. So I've moved it left, you're adding on 2. Perfect. So right 3, end up here. Excellent. Okay. Up to. No, we just did up to. We did up to and down. What else could we do left and right? Oh, we could do a stretch. So I'll stretch it, scale factor 2. Okay, so everything has got twice as far away that way. Scale factor 2. That's a hard one.
Right, so it's getting bigger.
Yeah, you need the brackets because we're inside.
Well, we know that, don't we? We're
Yep.
inside.
Yep, good.
So, and we know we've got x somewhere.
Yep. And I've
Now,
done
to
scale factor 2.
we want to think about the opposite.
Yep. Perfect. Yep, perfect. And then the easy one, actually, the easy one in this case, I mean, it makes no difference at all because, let me just, oh, hang on, we've got too many lines. What happens when you reflect a quadratic left and right over, this will show how well I drew this. If we flip it left and right, oh look, nothing happens because it's just reflected itself over. So actually, there's no way you can tell whether or not it's been flipped. And yeah, exactly.
That, wouldn't it? But then
Yeah.
a minus times a minus.
Yeah.
That's what squared means is plus. It's
Yeah.
still just x squared.
Exactly, that's why it's the same. Because what we've got here is minus x times minus x.
Yeah.
The minus and the minus make a plus, and then x squared. So actually, there is no difference between minus x squared and x squared. They're exactly the same. Okay, before we leave the quadratic, a little challenge for you. What if I go right 3, up 2? So I'm going to end up with the sort of bottom of the quadratic at 3, 2.
So you went
I've gone right 3
right 3.
and also up 2. Yeah.
Okay, well I can do the up bit really easily, can't I? So if it was just up 2,
Yeah.
it would look like x squared plus 2.
Yeah, that means up 2, you're right.
And if I was just looking at right 3, right is in that direction, isn't it? So
Yeah.
actually I want it to be y equals x minus 3
Excellent.
squared.
Yep.
Now can I just put those two things together?
Yep.
So I'd actually end up with y equals x minus 3 squared plus the 2.
Perfect. So when you see it written in this way, the quadratic, you can see what's happened inside. That's
Mhm.
gone right 3. And you can see what's happened outside. That's gone up 2. Do you know the name for this way of writing? You've written it like this essentially, x plus a squared plus b.
So completed square.
Completed square, yeah. This is, again, GCSE syllabus, but not everybody's seen it or confident with it. So this is the completed square. You should have done that in your holiday prep work for moving from GCSE to A level. So the completed square, we love the completed square, because the completed square shows us what the graph looks like.
Mhm.
So if we had one that was, for example, y equals x minus plus 2 minus 3, something like that.
Well, here, we know here, we had, if we've got a minus 3 here, we've ended up with a minus 3 here, we've ended up with a 3 here.
Yeah, so the
So,
graph
yeah.
starts sitting on, oh, I've lost my graph. The graph starts, we've lost a bit of graph, but never mind. We've lost all the graph. I'll put the graph back. The graph starts sitting on the origin like that, and, oh, I didn't do squared. Squared. So, we've got this bit inside, so
So
it's
that's to move up to
right
left.
or left? Left 2, exactly, and then this is outside,
So it's down 3.
down 3, exactly. So you can just literally take your quadratic and move it left 2, down 3, and then it ends up down there somewhere. So the completed square is a really nice shape for a quadratic to be in terms of sketching it. Right, let's just do a couple of examples. What would, if I write the thing down, then you see if you can move the graph. What would that be? Where would that be?
So that's an outside. So it's working as we expect it to, so it's going to go down 2.
Perfect. Easy, yeah?
Yeah.
Okay, and this one you might have to draw on.
So it's inside, so it's going to do the opposite. I'm useless at these.
So it's a stretch,
It's a stretch of,
and it's parallel to, maybe I should write this. It's a stretch. What's it parallel to?
the Y. No, X.
It's,
Definitely X.
that's it, it's inside, so it's the one that's left and right. It's not outside where we're looking up at the sky. Left and right, and that looks like the x-axis. So it's parallel to the x-axis, and it's about, so the bit that's fixed is the y-axis. And like you said, the scale factor is the opposite of what you think, so scale factor is half. That's it.
So it's going to be something like that.
Perfect. Perfect. And actually, if you're drawing this just, you can see everything's got half as far away from the y-axis. If we remove the red one, you can see it just looks like a normal cubit.
Mm-hmm.
So actually these structures with cubics and well, most graphs, you can't actually see unless you put both graphs on and kind of do a direct comparison of the two.
Yeah.
If you've only got one of them, you can't really tell whether or not it's been stretched at all, really. Okay, what haven't we done? What about...
So it's inside.
Yeah.
So we're going to do the opposite. So if that was going to move it 3 to the right.
Perfect. Easy peasy. Okay, this last graph is one that you may or may not have seen at GCSE. It's a reciprocal graph, y equals 1 over x, and this is what it looks like. Now, there are 4 parts to this graph, not 2. There is the line, the curve, and the other curve, but also these dotted lines, which are the asymptotes. So the graph is getting closer and closer and closer, but never touching the asymptotes. So if I start us off with a nice easy one, y equals 1 over x plus 2, then you should be able to move that graph. There we go.
Yep.
Perfect. Now you can see that the vertical asymptote is still invisible because it's on top of the y-axis,
Yeah.
so you can't see it anyway. But what was on the x-axis, that asymptote, has moved up with the graph. So you can now see it, and it's really important to draw it on. Similarly, something like, well, let's try this one. 1 over x plus 2 instead. What would that look like?
Well, that plus 2 is now inside, isn't
Yeah,
it?
it's gone inside. It's not, here's the 1 over x preserved, that's outside, but now what we've done is we've gone in here where the x lives, right inside. So you're right, it's going to move it left and right.
So and it's going to do the opposite to what we think.
Yeah.
So plus 2 is actually
Exactly, perfect. And now the horizontal asymptote is still on top of the x-axis, so you can hardly see it, but the vertical asymptote has now become apparent and is really, really clear. Okay, similarly to the cubic, when you do a stretch, you can hardly see it, but let's have a look what would happen. Let's do an outside one, 2 lots of 1 over x, which I could write like this.
Yeah.
Yeah.
Okay, I'm going to move back to where it was. If
Yeah.
I've got any other transformations on it. Okay, so it's a stretch and so
It's a stretch, good. How else do we describe it? Stretch.
And it is parallel to the y-axis.
Yes, because it's not inside, it's not down here. So it's outside, so we're looking up at the sky like a y-axis, so it's parallel to the y-axis, about the x-axis. And the scale factor?
2.
Excellent, 2. So everything gets twice as far away. Vertically, everything gets twice as far away vertically.
So that's going to stay where it is, isn't it?
Well, not quite, because it isn't on the x-axis, it's really, really close, but not on. Yeah, that's it.
Doing something like that.
Yeah, yeah. And you can see that if I now remove the red graph, your green graph will just look like a normal reciprocal graph. So you can't...
with the...
Yes, exactly. So you can't really tell with a stretch unless you put the two on top of each other for comparison purposes, which one's stretched.
That's a horrible one. There we go.
Yeah, perfect. Excellent. Okay, I think that's it for for the lesson, what you need to do is make sure that this page of your pack is completely filled in. You've got some examples, not loads, just a few examples. You don't have to write them all down, but the description is really important. What does this transformation do? So what does it do to the coordinate and what does it do to the actual graph? When you've done that, you're going to go on to the next video and we're going to talk you through the activities in your graph sketching pack.